Yes.
Yep, sounds good.
Okay. All right. The mic's on. It's after 1 o'clock, so we should start. So I will start, even while you guys continue. There we go. Thanks. Okay, guys. This is going to be very much describe it as a whistle-stop journey. Kind of picking up political jargon here. Talk about the inversion theorem, and that is a relationship between what we'll call the conditional value functions and the conditional choice probabilities. Maybe we need to turn this down just a little bit, I'm not sure. Oh, thanks. Identification of these models. In other words, is there more than one set of parameters that gives you the same data generating process? If not, if there are, well then we say it's not point identified. Okay? How would you estimate this model if you did not solve the conditional value functions? In other words, did not get that expected social surplus, expected value function, or social surplus function, goes by various names. Then moving into kind of an extension of that is, how many conditional choice probabilities do you actually have to estimate in order to estimate the parameters of the model? Up until now, we'll be using the conditional independence assumption that I described and Bertel was using through most of his talk. Can we relax that? And he'll introduce some unobserved heterogeneity. And then finally, want to describe, just show a couple of tables really, of some Monte Carlo exercises. I can really only give you a kind of a thumbnail sketch of each of these kind of concepts, and there's a version in the literature on different types of estimators that are in some sense pretty closely related or are CCP estimators to deal with these kinds of issues. Okay, so just as a reminder, we have either a finite horizon or an infinite horizon problem. An individual choosing between a bunch of different alternatives. Actually, the bunch of different alternatives could be changing through time. It wouldn't have to be the same cap J. Picking only one of them. We're going to have some observed stuff which we're putting on a finite grid. Putting on a finite grid, can we turn this down just a little bit? See whether is that still good for you guys up the back? Yeah, good. Now I'm not hearing myself spit. Throughout this talk, I'll be imagining just this is a grid, and in practice that's often true, but actually theoretically it's not based on that. We can easily put X in a Euclidean space. Indeed, if it's not a infinite horizon stationary model, and we're able to estimate what we'll call the appropriate CCPs, conditional choice probabilities, then we could even imagine this more generally as an information set that's growing over time. And in fact, some of the more recent work in this area is still working paper form. Looks at, well, what happens if you don't really know what X is, or it's a huge thing? How would you go about it then? And so those are some of the areas that people work on right now. And then this is the conditional choice probability the conditional independence assumption coming in here, where the unobserved stuff is, for now. Later I'll talk about unobserved heterogeneity, but for now, this is that type 1 extreme value or whatever it is. But the point is, the epsilons don't affect the future very much, only affect the choices, and the choices affect the future. We get data on the observed, what we'll call state variables, as well as the choices that people make. And then there's this, as I said before, mixed joint density function, but we'll also refer to it, with the conditional independence assumption wrapped into it right now, where you can see the transition of the future states only depends on stuff that future observed states only depends on currently observed states and the choice that you make. And the unobserved stuff only depends on the current value of the current observed state variable. So this is often called a taste shock because it really doesn't affect the dynamics of the problem except through the decisions itself. And it is just affecting the utility that you get right now. And it's a convenient thing to get around the problem that I talked about when everything is observed. And so you get no empirical content at all. You need something that's unobserved, otherwise you're going to run into a contradiction pretty quick if you're going to insist on empirical content. So here's our ex ante expected social value function, and sometimes called the social surplus function. The idea is, why is it social surplus? Well, what we're doing really is integrating over all those epsilons that are in the population. And so given this segment of the population with a particular value of x's, what is the distribution of epsilons, and what do these guys get when they optimize? Follow? Epsilons out there, we don't see, there's a distribution out there. Given a type of epsilon, they're going to make the optimal decisions. They're going to get value for the rest of their lives. We're integrating over that social. Okay, that's where the social surplus function name comes from. And we've got optimal decision rule. And one of the things that we're going to exploit in a big way is the relationship between what I'm calling the conditional value function. Bertel had a slightly different name.
Choice-specific value function.
There you go, choice-specific value function. Excuse me, I'm not up with them. And so you can see everything but the epsilon is in there. I talked about it first lecture. And I want to focus on the relationship between these V's and these P's. Okay? When I say these P's, I'm of course referring to the CCPs. And here, what we're doing is looking at what I'm going to call the optimal decision rule. Obviously, the optimal decision rule depends on both your state variables and your vector of taste shocks. That's what's going to produce the optimal decision rule. And we're integrating over the epsilons again, which are unobserved to the econometrician, of course, by assumption, to get these conditional choice probabilities. Okay. Now you can see that these P's are going to have to add up to 1. All probabilities do. And so, I hope, given their x's and given a t, okay, summing over j. And these b's, like there's a separate one for each j. Apart from that, the j and t's here, j and t's here, everything has looked nice. But of course, these v's are values. You never observe happiness. You only observe choices. So of course you're never going to get the value of the valuation function. You're only going to get differences between them. And so actually the number of things you can actually identify here is actually going to be the same as the number of things you can identify here. So the hope is maybe once you've got one, you can get the other. All right, here we go. Let's start out with the idea that we're looking at the difference between these two conditional value functions. And to make it simple, let's just talk about the difference between little j and big J. We could talk about any set of differences, but once you've got one set of differences, you've got them all. Okay, you can sort of norm by any of these ones. All right? Well, the conditional choice probability, CCP, is just integrating over this thing. Okay? And then we're asking, when is this, what does this mean? It's just an indicator function to say, well, it has to be that this plus this is less than or equal to this plus this for the j. Now, why is that true? I mean, really, we were talking about value functions or conditional value functions plus the epsilons being big or small. But now all we're doing is subtracting off the big J from both sides. Okay? So that's why we can put deltas here as well, and it's not going to make any difference. And so if we write this out, what this really means is we're integrating in this region. And then another way of writing this out is to say, well, let's look at the density of all the epsilons for the derivative, start again. Here's our densities for all the epsilons conditional on x at time t. Okay, this is the distribution function. Now we differentiate with respect to the little epsilon, with respect to epsilon j here. And that's what I'm calling big JG. And so it's just a matter of probability to show that this is equal to this, standard statistics. So what you've got here is a bunch of V's. Over here you've got some P's. And you're integrating over all the epsilons. And you've got as many differences as you have P's here after you sum to 1. All right? So let's take this just a little further. Let's think about a static model for a start. Static discrete choice model in which you get delta, if you take the jth, plus epsilon jt, which is the same epsilon as we were talking about before. If we thought about that model, static model, well then it's easy to see that this is the probability of choosing choice, making choice j in this static model when the payoff in this static model is just delta j plus epsilon j for the jth choice. Okay? So this is a logic in the case of type 1 extreme value. So basic point here is that this thing is invertible in delta. Okay? In other words, there are a bunch of deltas here, and here you can see them, all right, because we're normalizing by one of the payoffs, just as you would in a static model. And then we're saying, well, there are as many, for each x and for each t, there are as many deltas as there are p's. So this thing is invertible, which really means that if we just plug in the delta v's for the deltas here, we've got this result that the conditional value functions are equal to this q thing, the vector q, when it's inverted. Okay, so you already know how this works in the case of the type 1 extreme value, the logit model. And so it's just true more generally. So this Q minus 1 thing has an intuitive interpretation. Okay, we're taking the inverse of that Q that I talked about. Let's suppose that the agent is different between, say, the little j choice and the big J choice. All right? These are different. And so that means these epsilons have to line up so that this equation holds. Okay? And then we say, all right, well, that we just said is the delta V. All right? And here is the difference in the epsilons that make him indifferent between these two choices. Well, what is that? We just showed on the previous slide. That's equal to the jth component for the Q. Okay, so that's another way, that's a way, I guess you say, of interpreting what the Q minus 1 really is. So value of the Q minus 1, difference between the little j and the big J taste shocks, that make the agent indifferent between those choices. And so more generally, if we took the whole vector, then you could interpret these Q minus 1s as being a value of a vector such that the agent is indifferent between any of the choices. Okay? Why am I spending 15 minutes talking about this? Okay. First of all, if we use this result, we can get tractable representations of conditional value functions, meaning we can write down what the conditional value function is as a mapping from conditional choice probabilities and parameters in the problem that allow us to estimate it without doing any fixed point theorems or calculations. I'll describe that in a minute. But before we get there, this representation of the conditional value functions also tells us essentially how much we can identify and how much we can't identify implicitly, or at least something about that, from these kinds of models. Because there is the identification question. Is it really only one set of values that produces this data generating process? Or more? We get from this inversion theorem also different parametric forms that generalize the type 1 extreme value. I've already mentioned we estimate the model without actually solving it. And then there's a kind of a question, as I said before, with this finite dependence italics. How many CCPs do we actually have to get up in order to be able to solve the model? And, you know, the answer sometimes is almost all of them, or all of them, to be more specific. So it's not like this always works. And finally, there's an issue of, well, what about relaxing this conditional independence assumption, which the inversion theorem is making, you know, using like crazy? Can we get anywhere if we relax that assumption? Okay. So to get somewhere on the representation, the identification, I want us to define something called a conditional value function correction. See, here's the social surplus function, and here is a conditional value function. This social surplus function is, I am standing here with my x's and I'm thinking, what is my future lifetime choices when I make the right choice today and continue to make right choices in the future? Suppose instead I was standing in the same spot and said, I'm not even going to think about what those epsilons are today. I'm just going to take the jth choice. Okay? Don't blind me with extra information. And then I promise to be optimal. What is the difference between the value, expected value in lifetime utility under those scenarios? And of course, the reason I'm doing that is not because I expect people to be blinded because they don't want extra information, although optimal forgetting seems like a pretty good thing to think about as a research topic. The reason I'm doing it is because it's going to help us with the representation and the identification stuff. Well, I'm going to use this, and if we have the nested logit, it's going to take this form, okay? And you can show, Peter and I showed, sitting up the back there, that if you look at this conditional value function correction, it's equal to this form here, where here is the correlation between within the nest, okay, or the nest parameter, if you like. And so, if in fact there was only one nest, so this drop there, well then in the type 1 extreme value you just have this 0.557 minus log p being the value function correction. So that's the one we almost always use because we almost always do type 1 extreme value less logit. But if we went nested logit, that's how we go. And in fact, you can go a lot further than that, but I'm just giving you an example. Now, part of the reason I put up this example is because it shows what that value function is, and you can see that if you knew what p was, and it was just a standard logit, well, then it would just be straightforward. If you didn't know what sigma was and you were trying to estimate that, that would give you an extra parameter to deal with. Okay. So that's part of the reason I'm doing that. But part of the other reason is that this p thing here, this is just the probability given the x variables that you see that somebody makes the jth choice. So if you've got a lot of data sets are growing, and for each x you can get okay estimates of those conditional choice probabilities by looking at their sample analogues, or maybe smoothing over kernel. Because I said before, x's don't actually have to be discrete, although that's what I'm assuming right now. Then you just plug this p in here and you get this value function correction. In other words, that psi is identified. That's the point I eventually got to at the bottom of the slide. Okay? That psi is identified, this conditional value function correction. Notice that the assumptions that are used to get that, here we put a parametric assumption on this and we assumed that the parameters were non. See that? Is identified if I knew what sigma was in this nested, see that? And the reason I'm pointing this out is there's obviously a more general result going on in the background here. All right. So forget this maximization. Let's do it the following way. We got the conditional value function is equal to the current utility plus doing everything right in the future. Okay? But let's think about what that v function is. Go back one slide. That big V is equal to this little vj plus this thing over here. Okay? For any j, for any k. Okay? So instead of putting in big V, we could have written little bk t plus 1 plus little psi k t plus 1 in here to be equal to big V t plus 1 there. All right? So we could have written something that involves this and something that involves a conditional value function again. What do I mean by again? Here it is here for the t, and now we could have had a t plus 1 with a little nek there as well, and keep doing it. All right? So we're going to run it out to t. Let's imagine that we're able to sum. And in order to be able to do this, we actually have to be able to say that a sum is possible. So that's going to make it need to keep it away from infinity. In particular, we need to keep it away from going possibly to a positive infinity and possibly to negative infinity. So we're trying to add negative infinity to positive infinity. That's where we run into problems, okay? Doesn't have to be stationary at this point. Not for that part. And so we're summing over here, and we're getting utilities plugged in here with I used the letter little k when I went one step forward, but it could have been any of the k's. And we could have put essentially any weight on them, because going back to this step one more time, promise not to go to this slide, I think, any more times. We could have taken a combination of these guys and the same combination of these guys, and of course then we would have that the big V is equal to the combination of this sum, all right? And actually, we wouldn't even have to make those things, that combination, consist of just positive weights. Providing they sum to 1 so that we get the big V at the end, we're good. And so we can have negative stuff as well as positive stuff. We need to keep them bounded, of course. And so that's what these omegas are. Each of these omegas, when you put them together, they all sum to 1, okay? And then there's a kind of a transition, you know, and because now we're thinking we're moving the x's. We're moving the x's in a way we, the econometrician, say. This has nothing to do with the individual optimization. This has to do with us trying to estimate the model in an easy way. Okay? And we're imagining, loosely speaking, that we push these people down different paths according to the omegas, you know, with the weights going whatever way that we pick. And then we're also compensating them along the way with the size to say, yeah, I know you're not doing the optimal thing, but we'll pay you a psi as well. And in that way, they're getting the same overall utility as they would have got than if they'd just, after taking choice J, optimized from then on out. So that's another way of thinking about these conditional value function corrections. It's basically saying, yeah, we're going to make you go this way or that way or whatever way. The reason we're doing that is because we want to estimate you. We want to find out what parameters generated you. And so we've got to kind of set it up that way. You'll see that people do this all the time. And so in this setup, you've got utilities indexed by k, and then you've got these correction factors and weights that are directing people moving down the line towards the end of their life as they write out what their expected value of lifetime utility is going to be when they make choice J to begin with. Now, I haven't described yet what these kappas are, but they have a very straightforward interpretation. See, we have to get the utility that somebody gets in tau, and we have to ask, well, they'll have x in tau, perhaps, where x could be any one of these things, and they're going to take choice k at that time. What is the utility that they will get? Well, in order to do that, we have to ask, well, what's the probability that we'll end up in state, say, x I've got here, tau plus 1, given that we started out with xt, and we took choice j as well, and followed a sequence of omegas all the way down to tau plus 1. In other words, perhaps to be more notationally correct, I should have put up here as a superscript omega in brackets to indicate that the transitions that we will go through reflect the randomization, if you like, or the weights that we put on people walking down from point T to, in this case, T plus 1. And so this is just a standard Markov chain reflecting the fact that people are making choices. Here they were in tau minus 1. Here they are in tau. Well, what could happen? They could have come from any x tau. We have to worry about integrating over or summing over the x's they could be and the choices that they make at that point so that they end up at tau. And then we sum over the probabilities and we've got it. All right? One by one. Oops. I'll get there. Yeah. Thanks. So let's look at this. Let's look at the difference between the conditional value function at j minus the conditional value when you take choice j versus the conditional value function when you choice 1. I took a long time to explain this formula, all right? And what I want to do is difference this for j versus the same thing for little j equals 1. What do we get? Well, let's go back a couple of slides. I promised I wouldn't do it. Never believe me. Check it out for yourself. Okay. Remember that Vj minus psi j is equal to the big V. Okay? I'm going to use that in a minute because Vj minus V1 is equal to big V's cancelled out, psi j minus psi 1. See that? This difference is equal to that difference. Why is that interesting? Because this difference we already discovered is identified. Here it is. The Vj minus the V1. Then we've got the utilities, U1. And then we've got correction factors all over the place. They're identified. We talked about that before. No need to harp on that point. And then we've got U1s here. We already know that we're not going to be able to identify all the utilities because for every choice. Because I already said, despite Professor McCloskey's lecture many years ago on hills of happiness, that economists are about choices, not about happiness. And so you're only going to get those differences. And so it's with our laws of generality that we can normalize at each period in time for each set of x's, one of the utilities. Now, there's a little bit more to it than that, but this is the flyover, so I won't say any more about that right now. So we could set one of the utilities equal to 0. And normalize, and that's not, again, not quite right, with respect to everything else. We have to do something along those lines. And so if that was the case, where we said one of the utilities equal to 0, and, you know, in every application I've seen, that's essentially what happens. What you got is the utility of the jth term is equal to 0 plus, here are correction factors, here are correction factors, and here are these transitions. Let's just go back to the transitions. I know you're difficult to take those transitions seriously in a sequence of lectures like this. But look at what those transitions are. No, you're concentrating fully, yes. You see, these are just transitions on those state variables. You can clearly estimate them. They're clearly estimated. And in fact, Bertel was saying, you know, let's not talk about those because it's maximum likelihood estimators are really obvious. These kappas are just the weights that we pick. These are Fs that are identified and can be estimated either non-parametrically or, well, there's just sample averages or put a parametric form on them. And so they're obviously identified, which means that up to the normalization, I'm calling it a normalization regarding the fact that you have to normalize something, because you've got to get these differences in utility out. Up to that normalization, this is identified. UJs are identified, providing we know big T, we know the discount factor, we know the transition of the Fs, that is how the observed variables move to the next period's observed variables, and we know the distribution of the epsilons. Exactly point identified, meaning we have as many U's as we have P's. This has a nice closed form. The CCPs, in this case, with the conditional independent assumption, are a sufficient statistic for the sample. And that is given this one, but that also got a sufficient statistic with the sample itself. And so that is the sense in which we get identification. In other words, we have as many unknowns as we have parameters. So actually what we could do is, all right, here are our P's. We've got a big data set, imagine. Just going to take a sample analog here, take a sample analog here, form this guy, put it all together. Here we have our correction factors, put in the right spots. Then we have our U hat answer, okay? As many P's, as many U's. So the only way to increase asymptotic efficiency is to put parametric restrictions on the U, okay? Because this is exactly identified. So we do that all the time, of course. We do put parametric restrictions on the U's all the time. And the reason we do that is partly because of sample size, and partly because we see how these interactions work together, and so maybe we have intuition about how the parametric stuff should work. Yes, go ahead. Okay. So there's an existence theorem which says that, and it's a generalization of the inverse function theorem. Hadamard theorem is one way of doing it, but there are several ways of doing it, okay? Which says that subject to smoothness conditions about the epsilons, there is an inverse to wherever it is, this function. There is an inverse to that. That's an existence theorem, okay? Now, in the stuff that Peter and I have done, we go to the generalized extreme value case and show what has to be satisfied, and there it's a matter of numerically solving stuff once you get beyond nested logic. No one's really taken that up, and I keep encouraging people to do it. So next next chance to advertise, yeah, this can be done, okay? But the reason I showed you this example, of course, is because I wanted to show you how the P's and the parametric form interact. Notice that I just said with the inversion theorem that if you're not putting anything on the U's and you know the G's, well, then you're in good shape. What if you don't know the sigma in a non-nested, in this nested logic? Then you've got an extra parameter, right? So you need to put structure on it in order to go from there. Another kind of way of thinking about identification is what if you don't know the beta? Okay? Again, extra parameter. What are you going to do? Put extra structure on the other parameters. And so there is a trade-off here. And so in some ways, this identification theorem, if you like, wherever it is, here, is a statement, a benchmark of saying, here's a set of necessary and sufficient conditions. Suppose you want to identify more, well, then you're going to have to put some restrictions over here. Or, you know, what's the kind of balance, okay? So that's a way of interpreting what's going on here. Okay, yeah, microphone. Yeah, but start asking.
So for the part you define kappa, the transition
Yes.
thing, why do you use W instead of some optimal choice rule,
Okay.
D star?
Got it. See this omega here? Question is, why on earth am I just picking any omegas here rather than the D0 or the D optimal? Because D optimal I could have picked and didn't. Of course, if I picked D optimal, well then it would simplify a little, it would change things a little bit, not much. The reason is that as an econometrician, it turns out to be useful to pick omegas in different ways so that sometimes certain types of U's in here and sometimes they don't. Because look at this formula. It's basic, and then if we turn one more over, we've got this, where do we go? Actually, that's not a very good one, but I'll come back to it a little bit later. But for now, I'm going to say that if we choose omegas, I'm going to say cleverly, then it'll send people down certain paths as opposed to other paths, and we may be able to see lots of data on the paths that we do send them down, and so it'll be relatively easy for us to get sample analogs that make sense and go from there. Okay? Now, if we had lots of data, well, then there's an issue of, well, why would you ever worry about this stuff? And you'll see that in the identification theorem here, what I did was I just sent everyone down the first path. I could have sent them down any path with the correction factors in there, okay, in order to establish it. It's not that by sending them down different paths, I'll be able to get over-identifying restrictions. That's not true. But at this point, there's almost an element of the reason why I'm sending you down different omega paths is because I can. And later on, I'm going to say, look how helpful it is. Okay? Okay. Let's move on. How would you estimate these things in practice if you were using a CCP kind of format? Well, one way is to start out with the estimates that you've already got from the non-parametric stuff, back here. I'm calling it non-parametric, but unrestricted stuff, wherever it is. Here. Well, actually here. Okay. Start out with this guy, and then say, okay, let's impose a bunch of restrictions on it. Parameterize U. We've got a whole bunch of restrictions, weighting matrix in the middle. Why don't we do a minimum distance estimator on that? We can actually test whether the restrictions hold or not too at the same time. All right? That'll be one approach. And there's nothing special about doing that because people use what I'm going to call reduced forms all the time. And then, you know, originally when we're talking about those early Penn-Wharton models, whatever they were, they did just estimate what was called a reduced form model, and then they get that so-called structural model out by just imposing a few restrictions, go from there, right? It's well done, well known. So why don't we do the same thing here? Just to minimize this thing, just stacking these things according to a bunch of restrictions. And then we know the following. Suppose U, our systematic part of utility, is actually some kind of linear form, you know? U equals x beta. Well, it better not be beta. X gamma. Delta. I'm running out of Greek letters. But anyway, it's linear. Okay? Well, if it was linear, this is obviously a quadratic form. And this obviously has a closed form solution of the usual x prime x minus 1 x prime y thing, where you define your x's and y's appropriately. Okay? So that's a sense in which you could estimate your p's with these sample analogues, estimate your f's with these sample analogues, form your u like this. Now you've got the unrestricted. Bang it in. Impose your restrictions. Okay? That's one thing you could do. Another thing you could do is say, why don't we start out with a static model? Start out with a static model. Like, for example, in this logit case, something like this. In general, something like that would have this, where if it really was a static model, logit, random utility model, here's current utility from J, here's the sum of the exponentials with respect to K, all the others, logit, okay? Undergraduate. And then add in these H's things. Well, what are the H things? Well, think about what's going on for the individual. They're thinking, I don't just care about my current utility. Madison, Wisconsin, and DSE is a great thing after all, but maybe there's something else in my life as well that I'd like to do. So why aren't I doing it? And I'm thinking future, maybe? I don't know. Certainly not consumption benefits. So utility plus future utility, that is just the value function that you're going to get out of next period, basically. What are these terms? Well, the difference between action J versus action K is just the sum of all these correction factors appropriately worked through. Plug it in. This is a number, okay? This is a number. Because after all, you know what the P's are. You've already estimated them. You know what the kappas are because you plugged in your favourite choice of omegas and put them together with your F's. So you put a number in here, you put a number in here, do a logit. Okay? Or, I guess, you could say, here are our P's. We know how to estimate those guys. Let's simulate a lifetime path for these guys. Simulate a lifetime path. That's going to generate X's and D's, future state variables and future choices. From that, we'll be able to form an approximation or an analog, if you like. It's not quite an analog because we're using estimates that go in there of the expected value of the epsilon, given that the choice that the epsilon refers to is optimal and therefore taken. So this really is the optimal choice here. So we get those things out. Or actually, we could even simulate the epsilon itself and then go from there. And, oops. Here we would have the utility that's simulated out. We look at the different choices that are made. Again, plug a weighting matrix in the middle and get a simulated estimator out that way. Okay, so there are a variety of ways of going. Once you've calculated what the correction factors are, and that really does typically require a parametric assumption, and once you've got your conditional choice probability analogs along with the transition probabilities. Okay. So the big question really is how well does this work in practice? You've only got, every time I present this, you've only got a small number of data points for each x, and so those p estimates that you get, those conditional choice probability estimates, are really terrible, and they are going to screw up your estimates and also the whole world if you go through with this method. And so the question is, how much does that really affect things, and how far off do you go? Well, part of the answer to that question is, well, why don't you just do one step more with a Gauss-Newton step? And I'm not going to do that because Victor is going to do that. He's going to show you, he's going to say, okay, suppose you start, he's going to do more than that. But my interpretation of what Victor's going to do, and he's going to correct me, is that you could start out with some CCP estimators like that, or, and if you're going even with maximum likelihood, get some initial estimates out of the parameter values. They're going to be consistent, of course. And if there's only a finite grid, well, then they're also going to be asymptotically consistent. Although if in fact it's continuous variables, you would have to think about how you do a correction to do those kernel estimators to get asymptotic consistency. In other words, root end consistency as opposed to consistency. And then you could go from there, and there, after all, you would be locally within the true estimator, and therefore the policy iterations that Bertel was talking about actually would be valid, because theoretically at least, on a consistent setting, you would actually be just already within that neighbourhood. So a quadratic approximation would be good for both getting efficiency and also getting your policy iterations correct. So that is one answer. CCP stuff can be used as a first step towards getting a more efficient estimator, one way or the other. Another answer is, where is our precision coming from? Where is our misspecification coming from? Do we want the standard? Is it important that we reduce the standard errors more, or are other sorts of misspecification just as important? And that's something I can't answer here, but it is, I think, a reasonable question to ask. I want to move on to the question that you asked about why do we pick some omegas versus others, and so I prepared these slides for that question. So finite dependence is a useful way of reducing the number of pre-estimated CCPs. So imagine the following setup. You're going to send a person down, they take action K now, okay, action K now, and then you're going to send them down this path, all right? And it's going to produce a probability distribution over the x's in the future. Because after all, you're sending them down this path, you're choosing omegas for them. Here they go, out that way. And they end up with this distribution of x's after a while, after row periods. Or perhaps you're asking, what is the difference between this conditional value function versus this other conditional value function where you start them out on choice K rather than choice J? And so here we're going to send them down we start them out at K, we send them down another path that's generating, which to some extent we're controlling because after all we're picking the omegas for them too, so that after row periods the distribution of x's exactly matches up the distribution of x's that they would have done if you'd sent them down the J path. So you send them down the J path, set of omegas, eventually get to a set of x's, it's a probability distribution, send them down the K path, distribution of x's, suppose it's the same because you construct your omegas that way. From that point forward, they are solving the same problem because they're the same set of x's, at least in expectation, okay? So there's no difference between them. It's almost like things have rubbed out. Yes, it had an effect, qualifiers had an effect on the way you thought about things for a while, okay? But eventually, perhaps it rubs out, maybe because of where you've been shoved in and out of different kind of elective courses or whatever, okay? Circumstances. In any event, I'm the econometrician. I'm choosing those omegas. Yes, Rasmus. There's a mic, though. Maybe.
I'll speak up.
With a mic.
In this argument you're constructing, is this for a carefully chosen K and J, or are you making the assumption that this is true for any K and J?
Good. Okay. I am making the argument for a cleverly chosen K and J so that it applies to that pair of payoffs. Now, the more utilities for which I can construct those cleverly chosen paths and payoffs, then the more I can ultimately identify/estimate. Now, notice, though, that when I do those Ks and Js, we are moving through these different utilities here. And so it's not like I have a choice over that, because when I choose those paths, that's going to send them in different ways, and they're going to pick up different utilities. I'm explaining for everybody else too. And so that's the sense in which, yes, it is for a sufficient it is for specific Ks and Js. It might not be for all of them. And then there's going to be a question, how many equations do I get out of this? And do I have enough equations relative to the number of parameters I'm planning to estimate? In other words, what kind of restrictions am I going to put on these U's so that I can still estimate the whole thing? Follow up.
I should have held on.
Yep.
Can you give a practical example of instances when you know how to identify those Ks and Js?
Yeah, I think I can, by extending the example I'm about to give.
Okay, all right.
Okay, come back to me if I don't. I'm going to try. First of all, I want to talk about terminal choices. Okay? And so suppose there's a terminal choice, which means that I exit the industry. And so I have a choice of either staying in the industry or exiting the industry. Now, once I've exited the industry, I get my scrap value, but that's it. Okay? No more problem to solve for me. So imagine two firms, one of which is going to exit now and the next one is going to exit one period from now. We have to worry about what's going to happen now and also one period from now, but no more, nothing else. Okay? And so in a minute I'm just going to have some algebra that kind of cleans that up maybe. But let's suppose we expand the choice set now along the lines that you were saying, hey, does this always work? Question. Well, suppose these guys have other choices as well. And suppose, for example, they can perhaps invest or not invest. And suppose the guys that invest actually can't exit or something along those lines, and so that terminal choice thing is not available to them right now. They're somehow caught. In that setting, how would I then think about the utilities that you get from investing versus not investing when I don't have the terminal choice of being able to exit? Now, I'm not saying you can't do that, but I am saying here's a setup where we've got a terminal choice. Suppose that terminal choice didn't exist for some of the state variables. What would we do then? Then we would have to think about moving in some other way. Now, that doesn't mean that we couldn't, because I'm doing this on the spot, of course. But that's how to start to think about what's going on here. Okay? Well, okay, the point about the terminal choice is that it really doesn't matter what the transition is after you've when you choose when you choose choice one. What happens to you afterwards does not depend on your state variables. That's the key here. That's the key for terminal choice. I gave scrap value as if it's constant, but basically it's a process that doesn't depend on the past. And so if we're thinking about what's going on in that case, and we're asking what's going to happen in 2 periods from now, it simplifies to this when you take the terminal choice. Okay? And so if we go back to this representation of utility that I talked about, that was way back on, a few slides ago. I won't go back now. Well, then what you would get, and this is really the answer to your question, the difference between these utilities, J and 1, depend on these correction factors for J and 1. And then what happens in the future, but what happens in the future only really depends on what's going to happen next period as well, given this set of choices that I've assigned to these guys, which are not optimal, but I've got the correction factors in there, so I'm dealing with that. And so now I've got them in here, and I just have to worry about next periods, what's going on, as opposed to following period, blah, blah, blah. Okay. Here's one more. Mr. Zerker's problem. Job matching problem too, actually. You got a renewal choice here, okay? And basically what's going on there is that if I replace the engine with a new one, it doesn't matter what the condition of the old engine was. It's irrelevant. It's being scrapped. It might be really good, really bad. Who cares? It's future that counts. And so in that case, again, you've got a situation where what you get in xt plus 2 from now, given that you don't replace this period, but you do replace next period, just depends on the distribution of that new engine 2 periods from now. And in this case, not going to go through it again, but basic point is that with the renewal, you get a slight difference in the formula from, you compare this line there with this line there. You do get a difference because it is renewal, okay? But when you, again, apply equation 4, you get this difference, okay? Just take it from me for now. Oops. So both of these, terminal choices and renewal choices, are used all the time in empirical work. And it's partly because they're tractable. Last part. I want to briefly touch on unobserved heterogeneity. I said flyby, flyover or something. Now let's relax this last assumption, that the conditional independence assumption. Let's try and ask, can we move beyond the conditional independence assumption without solving the model? Okay? Walpin and I already tried that. Packers did some stuff, and people still do it with some unobserved heterogeneity in there. So it's not like it can't be done. But as I said in the end of the first lecture, there is really a trade-off between how many observations, what kind of complexity of model, etc. Okay? How would you do this? Well, for a minute, let's suppose we actually knew what these p-values were. I mean, this is completely wild. There's no reason why you would know them. You don't. But it's just a way of motivating what we're about to do now, okay? Well then, what you're trying to estimate here is the probabilities of these different types, say, okay, which you don't observe. I'm going to generalize this in a tiny little way in a minute. And at the same time, you've got these probabilities of different types, as well as the thetas that drive the, utilities. Okay? So here's our kind of logit thing. Okay? Kind of logit thing. Because you can see the logit stuff here. Okay? And over here. And what we've done here is put in a renewal type setup, okay, to deal with the fact that we're dealing with that we have that H correction. Okay, so it's not really the likelihood, not the likelihood, but this quasi-likelihood that I was talking about before when I went through the second method. And we're just plugging those in, and then again, this is clearly just a logit in that case. That would be how we could go. And so if we put this guy in here and maximize the whole thing, that would give our not really maximum likelihood estimators, not at all maximum likelihood estimators, because we're plugging in these P's, if you like, or if you like, fake maximum likelihood estimator, because we're plugging in these P's, the values that these P's take, right here. Okay? But then just doing a logit, except it's not a logit because we've got the sum of logs over here, which is a pain. And so then we say, okay, let's do something easier than that. Why don't we define what we'll call first of all, we have a look at the what an agent does. He's an S-type agent, and we see his whole sequence of choices and his whole sequence of X's. And so from that observation on the individual for the whole of his path, we make some kind of inference about what he must be. Changes his job all the time. Clearly loves leading lots of people, or or other people can't stand him, which is, it's not quite sure which one is which, right? But in any event, we're imagining that these people are different types, and we look at the whole path, and then we make inferences about what type of person they are. And that's what the DN is in there, see? The path that we see for this person all the way through. And we're thinking, well, if we knew theta and we knew pi, well, then we could form a conditional probability of him being a particular type of person. And here it is. Okay, this is a particular type of person, given that he has these kinds of, given that we have these paths, and here are this, given that he has these kinds of paths, well, what other types could he have been? Okay. And then, if we knew this, we would then go ahead and say, all right, we don't exactly know what type of person you are, but we have some probabilities on you. You could be, to turn it into the Harold Zerker example, you extended, you could be a Ford or you could be a GM. This is clearly a counterfactual because he only had GMs. But leave that aside for a minute. And we're going to see from the sequence of bus engine replacements whether you're more likely to be a Ford or a GM, because Fords might have different costs of replacement and also different maintenance costs from GMs. And so we could see from the sequence a little bit about what type of person you are. If we knew what type of person you were, well, then we would know what this was, and this would either be a 0 or a 1, okay? And we would be right back to the original case. Because if we knew what was going on, well, then we would know the posterior on this conditional, and it would be telling us you're definitely a Ford or definitely a GM. We'd just be plugging in Ford or GM here, that's what the S stands for, and then corresponding here is 0 or 1, okay? But since we don't know, we're just weighting it. Maybe 3/4 Ford, 1/4 Ford, 1/4 GM, something like that, that's coming from this. Now notice that this is coming from an iterations here. You know, the iterations are the m+1 iteration. What's really behind this? Well, we're plugging in our previous estimate of theta and our previous estimate of the number of GMs there are, the number of Fords and GMs there are, that's the mth iteration. And so then we're updating each of these and going from there. So that's part of the iteration. So step 1, at the m+1 iteration, compute this guy, then compute the average over all of these people to get the average over the whole fleet of buses, and then update according to 1 or 2 rules that we're going to use in a minute to get the P's. And having got the P's, then we just go ahead and maximize. All right? Again, and that gives us the next set of thetas. How do we update the P's? Well, one way you could do it is with this fake likelihood. It is a fake likelihood, not a real likelihood. Because we're putting in previous estimates of P in that quasi-likelihood estimator that I talked about before, in which we plug in those H hats. You're probably lost with the notation, but the futures in there, and last period thetas, okay? And alternatively, we could just look at, well, how many Fords are there? Well, we just add up all the averages, all right? And then to get what is the expected number of Fords that we've got? And of the expected number of Fords, how many of them replaced engines? To get that, okay? And so that's how we update this. Again, pretty simple in terms of algebraic stuff. So what I want to do now, in the remaining 3-4 minutes, is just give you a sense of how this works out in a couple of Monte Carlos. All right? Go back to Mr. Zerker. Here is mileage, which is driven by some observables. This delta thing is a root thing that's observed by us too. And then, but also there's a disturbance that sort of varies the amount of mileage that you add each period. Okay. There's the transitory type 1 extreme that's usually tacked on in these kinds of setups. And here is our unknown. We don't know whether it's a Ford or a GM. Okay? And so we're going to estimate it using the methods that I've talked about over this lecture. We've got the difference between the utility of not replacing versus replacing is just parameterized this way. And so with this renewal probability, what we get is, here's the conditional value function minus for replacing versus not replacing, okay? We just plug in the appropriate utility difference here, as well as worrying about the one period, what's going to happen one period from now, because we've got a renewal thing, and that's why we only have to worry about what's going to happen one period from now. Plug that guy in. And here's what we get. We're talking about 50 simulations, 1,000 buses, 20 periods. We're estimating the discount factor as well, okay? So this is an important difference between some of the stuff that Bertol was describing and what we're talking about here. If we do full information maximum likelihood, at least back in the early 2000s, it was 2 hours, okay? Now, it's nowhere near that now, but it's still minutes. No question about that, because my students do exercises on this kind of stuff. With the CCP, if you knew the S's, yeah, S's observed, see whether you know whether it's a Ford or GM, it comes back to a matter of seconds, okay? Then if you ignore S, you go wildly off base. So if you ignore unobserved heterogeneity that you think is important, you will get biased estimates, okay? In the sense that the estimates that you get won't be that useful because they really are affected, okay? So we check that out. And when S is unobserved, you can see that the time doubles for a full information maximum likelihood goes up quite a lot for CCP. It goes up to 6 minutes here, okay? And that's because you're redoing things all the time, backwards and forwards as you go through that iteration thing. But the iterations themselves are pretty cheap, so they don't take very long. And then we also decided, well, okay, we'll fancy this model up just a little bit by imagining that this thing is changing because there are costs that might be going on, okay? Costs over time, and so perhaps Mr. Zerker can see those costs. We can't. That would be a problem for maximum likelihood because you'd have to put a parametric distribution on it. With CCP, obviously you don't. You're just estimating these things as constants. And so in that case, you get an increase in time, but not huge. Very last one, and I'm going to pretend that I can carry what was short from one lecture to another by just a couple of minutes, if that's okay. I'm not sure, making up the rules. It's like... I won't test too much. Last Monte Carlo, okay, IO. All right, we got some entrants coming into the market. The entrants got to pay costs. Incumbents don't. Okay. Setup cost transforms entrant into an incumbent. All right, so you pay setup cost once. However, there's only so many slots. Think of strip mall, which is kind of a 20th century thing, but they still exist. So there are so many slots where you can put in an extra place, okay? If it disappears, if someone disappears, well, next period someone can come in to replace it, all right? So land has some value in this. So two sources of dynamics. I mean, you could argue that perhaps. Firstly, the entrance depreciating the startup cost over the anticipated lifetime. That's one thing that's going on. And then the other thing is becoming an incumbent reduces the probability that other guys will come in the future because there's one more guy in there and it's like, oh, do I really want to compete in this crowded field? Okay? So I like to say CCP is burgeoning literature, but not that burgeoning. All right? It's not too crowded. So that's the sense in which you've got a strategic aspect to this as well. So each market has a permanent characteristic in this world. Separate markets, they're all playing the same equilibrium, okay? You've got the number of firms being a demand indicator of what prices are going to be like if you come in, if you play that way. There's an unobserved state variable, and this is the S part, the unobserved state variable that's moving around. It is exogenous. If you made it endogenous, conceivably you could do that, but we're talking about something that is much more, I'll say, complicated in terms of what you have to compute and also the number of observations you need to get anywhere. And it's a very simple one because down the diagonal you have pi's, and in all the off diagonals, they're the same. Okay, and so there are 5 separate states, so in all the off diagonals, it's 1 minus pi times 4. So that is the parametric assumption we're making on this state variable. Remember I said before that these models are only identified up to the distribution of unobservables. Now I'm putting unobserved heterogeneity in there as well, so clearly there's a question of what's identified and what's not. There's a whole lot of parametric structure on this. You can see that. Here is the price data that we're assuming. And you can see the price is going to be falling with more people in there because alpha 3 is negative. And so there is also, in addition to price, there's gross revenue, so costs. It could be imagined gross revenue would be, or net revenue, I should say, is equal to gross revenue. That would be price, say, minus costs. Normalizing the exit utility, type 1 extreme, at most 6 entrants, simulating for 3,000 markets. Here we're not estimating for here we're not estimating the discount factor, and so starting out with 6 entrants, we just ran it 4 to 20 periods to try and settle it down in a stationary kind of world. It did after about 20 periods. And here are our numbers at the end of the day, and you can see I'm up to slide 31 and way over time. This should be a minus 0.5 here. I didn't bother saying with the earlier CCP, but if you look at it, you can see the numbers for either a CCP estimator or full information maximum likelihood. They're pretty close. And you can see here too that these numbers are pretty close to what they should be. As I say, this is a minus 0.5. You can see the amount of time it takes. We've tried various different, several variations on this. I think I should pull up. Thanks, guys.